Okay, let's have some fun with drawing Lewis structures. Here I have this recipe for making Lewis structures, and it's not going to include some more complex examples that require formal charges for checking or expanded octets. This is just a basic lesson in drawing electron-dot formulas. You know that Lewis dot formulas are important because they represent valence electrons, and valence electrons are important because they're the ones involved in reactions, bond breaking, and bond making. Hey, that's the chemistry that we all know and love. Lewis structures are also important because they're kind of the first step in giving you an idea of how to arrange the electrons using valence shell electron pair repulsion theory to obtain a good 3D geometry or good estimate. 3D geometries are important for molecules because that really dictates their chemical and physical properties. Okay, let's go ahead and take a look at our first example. Let's try CO2, carbon dioxide. So according to this first step in my recipe, you add up the number of valence electrons. Carbon has 4, oxygen has 6, and there's 2 of them. That's 12 for a total of 16 valence electrons. All right. Now, we're going to arrange this molecule so it's somewhat symmetrical because nature loves symmetry. So we'll put carbon in there. Also, carbon is the least electronegative. That always goes in the center, except if there's hydrogens involved, which isn't this example, but hydrogens go on the outside. We'll take a look at an example later of that. All right, now the next step is to put in the single bonds for the molecule. So carbon is bonded here to the oxygen, and that's a 2-electron bond, so that counts as 2. This is another 2, so that's 4 total. And then we distribute our remaining electrons as non-bonding pairs. Usually we do that on the external atoms first. So I have 2, 4, 6, 8, 10, 12, 14, 16. Now we're done with all the electrons. The next step is to check the octet rule. The octet rule is important because atoms tend to react to form a stable octet of electrons. So we come back here and check. This oxygen has 2, 4, 6, 8 electrons associated with it, and so does this oxygen over here. But as you see, carbon only has 2, 4, which is no good. So we need to go back and make some multiple bonds so that carbon has the full octet of electrons. So we see that we can move this lone pair in this position, making a double bond here, but that's still not going to be enough, so we need to move in another lone pair of electrons to make a double bond here. Our new Lewis structure then would look like this, and in this Lewis structure we see that the octet is obeyed not only by the oxygens 2, 4, 6, 8, but also the carbon 2, 4, 6, 8. So this is a valid Lewis structure. All right, very good. Our next example is a little more complex. It involves resonance structures, and we'll see how that comes about with SO2. Again, we add up the valence electrons. Sulfur has 6, plus oxygen has 6, 2 of those. And of course that's going to be a total of 18 valence electrons. Now we just need to make it symmetrical because nature loves symmetry. Do our single bonds first. 2, 4. Distribute the rest. 6, 8, 10, 12, 14, 16, and 18. So that last lone pair of electrons needs to go on the sulfur. The next part of the procedure is to check the octet rule. We see it's good here, 2, 4, 6, 8, same over here, but sulfur has only 6, 2, 4, 6 electrons associated with it. we're going to need to make some multiple bonds. The question is, do we move this one in to make a multiple bond or this? I guess the answer is we have to do both. And the true structure is going to be an average of these two what's called resonance forms of the Lewis-Dot formulas. So let's take a look at what that would look like if we moved in, say, this bond here, or that lone pair to make a bond there. Our new Lewis structure would look something like this with a double bond over here. And now sulfur's good. It has 2, 4, 6, 8 electrons. 2, 4, 6, 8, 2, 4, 6, 8. But there's another possibility that make up the total possible resonance forms for this structure. Some will have more than 2, 3, 4, or whatever. The other possibility comes about from moving in this lone pair of electrons instead and not this one over here. So that Lewis structure is going to look just like this. And so now we have our two valid Lewis structures. The octet rule is obeyed, and the true form is thought to be some average between these two Lewis structures. All right, our last simple example for finding Lewis-Dot formulas is water, H2O. This is pretty straightforward. I have 2 electrons from the hydrogens, 1 each, plus my 6 on the oxygen, 8 total valence electrons. I'm going to put the least electronegative in the center, except with the hydrogens. They always go on the outside. So by default, oxygen has to go in the center, make it symmetrical. Distribute bonding electrons. 2, 4, non-bonding. I can't put any more on the hydrogens. Hydrogens can only have 2 electrons associated with them. So I have to put those lone pairs here, 4, 6. So that's 2, 4, 6, 8 total electrons. So they're all distributed. And my octet rule is good for the oxygen, 2, 4, 6, 8. Hydrogen only needs 2. So this is my valid Lewis structure. Just as a prelude to maybe a next possible video, you would use this along with valence shell electron pair repulsion theory to tell you that there's 2 non-bonding electron domains, 2 bonding electron domains, and of course that would give you a tetrahedral electronic geometry or a bent molecular geometry for water. I hope this has helped in some way, and thank you for listening.